Welcome to the session. Today we are going to discuss Module 3, Algebraic Structures and Combinatorics. In that module, we are going to discuss the question bank questions. See here the first question. Solve Z, star B in a abelian group, which is going to be show that it is an abelian group where Z is a set of integers and star is a binary operation defined as like this. So it is going to be defined like this. Z is a set of integers. Now star is defined like this. Now we are going to verify Z, star is an abelian group. So for that, let us discuss all the things. So first of all, it should be a group. After that, the commutative law is force. Then we can say that Z, star is an abelian group. So first of all, we are going to prove that Z, star is a group. So is group means now we are going to prove that it is going to be closure and it is going to be associative law and it satisfies existence of identity and inverse. So whenever the binary operation or star is following these four conditions, then we can say that it is a group. So after that, we are going to verify whether it is a satisfies commutative law or not. So first one is, we are going to discuss about the first property. So that is nothing but a closure axiom. So in that closure axiom, so here it is given, let us say A is an integer, B is an integer. So I am going to take it as A I am taking, B I am taking, let us say which are elements in Z. Then obviously A and B are integers which are belongs to Z. Then A minus B is also, or A plus B is also integer. So then this is also belongs to Z. So now 3 is also one integer. Then we can say that A plus B and minus 3. 3 is an integer. Then this is an integer. Subtraction of two integers is again integer. So this is also belongs to Z. Now let us go for A star B. Now we are going to take it as for every A comma B belongs to Z. For every A comma B belongs to Z, then A star B is equals to A plus B minus 3. A plus B minus 3. Already we said that A plus B minus 3 is belongs to Z. So we are going to say that this is belongs to Z. So that means A star B belongs to Z. This implies we can say that this is a star is that means the binary operation is closed. Or we can say that G is closed, or we can say that Z is closed under the binary operation, star. And this is the first axiom, and the second axiom is associative property. Associative property. So associative property, for that we are going to consider any three elements. Let us say A, B, C belongs to Z. A, B, C belongs to Z we are going to take. And then, so here we are going to take it as A star B star C, which is equals to, so this binary operation is going to be defined like this. So which is A plus B minus 3. A plus B minus 3 star C. Then this is again I am going to take it as this is A and this is B. So once again A plus B. So A plus B minus 3 plus C and minus 3. So this is nothing but A plus B plus C minus 6. A plus B plus C minus 6. So now similarly we are going to take another one is A star B star C, which is equals to A star B plus C minus 3. So then it is nothing but A plus B plus C minus 3 minus 3. This is also equal to A plus B plus C minus 6. Call this as equation 1 and this as equation 2. From these two equations, we can say that A star B star C is equals to A star B star C. So whenever this is going to be satisfied, then we can say that Z is associative. Z satisfies associative law. Z satisfies associative axiom under the binary operation. Then star. So now we are going to discuss. So the Z comma star is satisfying closure and associative. So we are going to say that Z comma star is a semi-group. Now let us say whenever if it is satisfying these two, then we can say that is a semi-group. Now we are going to discuss afterwards the remaining, the third property. So it is existence of identity or identity axiom. We can say that identity axiom. So now identity axiom means let us we are going to take E be the identity element. Now we are going to verify whether E belongs to Z or not. If E belongs to Z, the corresponding value, then we can say that the integer set will have the identity element. So E be the identity element. Then we are going to consider. Let us say any element we are going to consider. So that element is A belongs to Z. We are going to take A belongs to Z. So now A star E, which is nothing but A plus E. What is that? A plus B. What is this? A plus B minus 3. So what we are going to say? When E is the identity element, whenever A star E is equals to E star A is equals to A. Whenever this condition is satisfied, then we can say that E is the identity element. Suppose if I am going to take it as A star E is equal to A, which implies A, then another one is A plus B minus 3. So A plus E minus 3 is equal to A. Then A get cancelled. So E is equals to 3. So it is a set of integers. Now we are going to say that E is equal to 3 is also integer. So definitely it is a member in Z. So we can say that it has the identity element. So we are going to say that Z comma star is monoid. Now let us go for the other one is the inverse axiom, existence of inverse or inverse axiom. So now let us go for, let A belongs to G. Then if A belongs to Z, now we are going to prove that A inverse is also belongs to Z. So A inverse should be a integer, then only it is belongs to Z. Now let us go for, so A inverse, A star A inverse is equals to A inverse star A is equals to the identity element which is equals to 3E, and E is equals to, of course, the value is equal to 6. Now let us consider any one of this. So now I am going to take A inverse is equals to E, but E is equal to 3. Then if I am taking like this, then A plus A inverse minus 3 is equals to 3. Then this will become A plus 1 by A plus 1 by A, or else I am just taking it as, then we are going to consider A plus A inverse is equals to 6. Then A inverse, which implies A inverse is equals to 6 minus A. So here A belongs to Z. A belongs to Z means A is an integer and of course 6 is also an integer. So the whole thing must belongs to the integer set. Must belongs to integer set. So A inverse is equals to 6 minus A belongs to Z. So we can say that Z comma star is a group. Z comma star is a group. Now, so we are going to prove that it is an abelian group. It is an abelian group. So we are going to discuss about the other property, commutative property or commutative axiom. So now we are going to discuss the commutative property. So for that, we are going to consider A comma B belongs to Z. A comma B belongs to Z. Then A star B is equals to then A plus B minus 3. A plus B minus 3. This I am going to write it as B plus A. A is an integer, B is an integer. So A plus B can be written as B plus A minus 3. So this is nothing but B star A. This is nothing but a B star A. So A star B we took and it is equals to B star A. Then we are going to say that Z comma star is a group as well as it is satisfying commutative. So we can say that it is an abelian group. It is an abelian group. So like this we have to discuss. So for proving, first it is an abelian group. For that we are going to prove that Z comma star is satisfying closure property and associative property. Then it will become a semi-group. And apart from that, Z comma star is a semi-group. If it is having any identity element, then it is a monoid. Then Z comma star is a monoid. And if it is having inverse element, then we can say that it is a group. And Z comma star is a group and it is satisfying another property, commutative property. Then the group is known as a abelian group. The group is known as a abelian group. Like this we have to solve the problem. Now let us go for the another one. So here this is if circle B is an operation on Z and then which is defined as X circle Y is X plus Y plus 1. Prove that X circle Y, Z comma circle is an abelian group. Is an abelian group. So here also the integer set is defined as Z and we are going to prove that. So earlier we have to prove A plus B minus 3 and here it is given the binary operation. We are going to consider it as a circle is the binary operation and we are going to prove that it is an abelian group. So for that, first of all, we are going to prove that it is closed. So for that, it is closure axiom. So for that, any two elements we are going to take and between them, the binary operation circle. So we are taking X comma Y belongs to Z. So what is X circle Y? X circle Y is X plus Y plus 1. X circle Y is equals to X plus Y plus 1. So X is an integer, Y is an integer. So X plus Y is an integer, plus 1 is also integer. So we can say that X circle Y and belongs to, then we are going to say it is a Z. So we are going to say that Z is closed under the binary operation circle. Under the binary operation circle. Next we are going to prove that associativeness. So for that we are going to take three elements. Let us consider X comma Y comma Z belongs to Z. X comma Y comma small z. X comma Y comma small z belongs to integer set capital Z. Then we are going to prove this is equals to this one. So for that, X circle Y circle Z is equals to Y circle Z is equals to this one. So once again X Y, so X plus Y plus 1 and once again X plus Y plus Z, Y plus 1. This I am going to write it as X plus Y plus 1 plus Z and that can be written as like this. So this shows it is satisfying associative property. Now we are going to discuss whether it is satisfying the identity element or not. So for that we are going to find out whether it is having any identity element or not under this operation, under this binary operation. So for that, let us consider -1 is an integer. So definitely it is also a member It is also a member in Z. So x circle minus 1 is equals to x plus y. This is y I am going to call it as. So x plus y plus 1. So simplifying this is equals to x. So what we are going to write? X circle y is equals to x. Y circle x is equals to x. Then we can say that y is the identity element. Y is the identity element. So or else E we are going to take it as, let us say x into E and x circle E and E circle x. If it is equal to x, then we are going to say E is the identity element. So now what we are going to get? X circle E is equal to x and E circle x is equal to we are going to get x. So in the place of E, whatever we have, so minus 1 is the identity element in Z under the binary operation circle. Now up to this we are going to say that the Z comma and circle is a monoid. Up to these three satisfies. Whenever these two satisfies, we can say that Z comma circle is a semi-group, and after satisfying this, we can say that it is a monoid. It is a monoid. Now, taking the monoid, and if it is having any inverse, then we are going to say that that monoid is a group. That monoid is a group. So here, let us, I am going to take for any x belongs to Z. So means that x is an integer. So that x is an integer means minus x is also an integer. So then minus x minus 2 is also an integer. So this I am going to write minus of x plus 2 is also an integer. So definitely it is also belongs to Z. Definitely it is also belongs to Z. So we are going to take x circle minus of x plus 2. So that is nothing but x plus y plus 1. So which is equals to minus 1. So when we say that the element y is the inverse of x, if x circle y and y circle x is equals to the identity element, What is our identity element is minus 1. So what I am saying that x circle y circle x then is equal to minus 1, then y is the identity element, y is the inverse of x, or x inverse is equals to y. So for that sake, this y we are going to take this as minus of x plus 2. So now x circle y is equals to, if you are going to apply x plus y and plus 1, so I am going to get the identity element. Similarly, y circle x, so this is, consider this as y, then this is, I am going to take it as x circle y, then y circle x. So if I am going to have the identity element, then we can say that y is the inverse of x. In the place of y, what we have? Minus of x plus 2. Then we can say that z comma circle is a group. So after that, if it is a group, then if it is satisfying commutative property, that is nothing but x circle y is equals to y circle x. If it is satisfying, then we can say that the group is a abelian group. The group is an abelian group. Okay. So for that reason, we are going to take any two elements x comma y belongs to z. Then we are going to take x circle y. So x circle y is this, and we are going to interchange. Anyhow, x plus y plus 1 is equals to, we are going to write y plus x plus 1. So that is equals to y circle x. So this is by the binary operation, circle is commutative. Then we can say that z comma circle is an abelian group, because it is automatically is a group. So group is satisfying a commutative property, then that is nothing but a abelian group. Like this we have to do the problem which comes under this. Now let us go for the another one. So here we are going to discuss, show that for every binary operation q minus 1 and defined by a cross b is equals to, like this is the definition. So cross is nothing but the binary operation, and Q is nothing but a set which is nothing but which is Q is just we are going to consider a rational number. Q is here we are not going to define anywhere. So Q is a rational number. Q rational number set. Rational number set. So in the rational number set, where it does not consisting 1. It does not consisting 1. So in the rational number set does not have 1. So then it is going to satisfy the commutative, associative, and closure, and next identity element, and next inverse. So we are going to prove that it is a group. It is a group. Of course, we are going to find what is the identity element and what is the inverse of the given element A. So for that, so for beginning, let us go for G, the given set, whatever the given is Q minus 1, we are going to take it as a Z. Let us say a non-empty set, which is nothing but a rational number set, but it does not have a 1. So that's a set, we are taking it as G. So then I am going to take A and B belongs to G, 2 elements. I am going to take A and B belongs to G. So whenever A, B belongs to G, definitely A, B are 2 rational numbers, and A and B both are not equal to 1. Both are not equal to 1. So because G we are taking, it is not consisting 1. So and A and B values also rational numbers, and they are not equal to 1. They are not equal to 1. Now the closure axiom. So the closure axiom, now we are going to verify the multiplication. We are going to verify multiplication defined on the set G. G is nothing but Q minus 1. Q minus 1. So now we are going to prove that what is it satisfies the closure property, associative property, commutative property, identity 1, and the next inverse. So that means it is nothing but a abelian group. It is nothing but a abelian group. Now let us go for closure axiom. So closure axiom, let us consider A comma B belongs to G. Now we are going to prove that A into B belongs to G. Then we can say that G is closed under multiplication, under into. And here A into B, then which is defined as A plus B minus AB. A plus B minus AB. Then what is A plus B minus AB? A plus B is again a rational number. A is a rational number, B is a rational number which is not equal to 1. So definitely A plus B is also a rational number which is not equal to 1, and minus AB is also a rational number which is not equal to 1. So we can say that A cross B belongs to G. A cross B belongs to Z. So that is nothing but it is a closed one. It is a closed one. So G comma is closed. Now we are going to verify the next one. Suppose if we are going to say that if it is having, suppose we don't know, this is AB. AB value, of course, it is not equal to 1, and A plus B is also not equal to 1. Subsequently, directly we can say that G comma class is closed. Or else, suppose if you are having any doubt that A plus B minus 1 value will become 1. So for that logical thinking, so to avoid that, we are going to take it as let us assume that in a contradiction manner. Suppose A cross B is equals to 1. A cross B is equals to 1. What is A cross B? Is nothing but A plus B minus AB is equal to 1. So from this, I am going to take it as, I am going to find out what is the B value. What is a B value? So here, I am going to take it as A cross B is equals to 1. So what is A cross B is nothing but A plus B minus AB is equals to 1. So then I am taking B 1 minus A is equals to 1 minus, it is 1 minus A, and next B is equals to 1 minus A by 1 minus A. This is equal to 1. See, if I'm just taking A into B is equal to 1, if I am going to take, then what I am going to get? B is equal to 1. So what is my assumption? A and B values, if I am going to consider in G, definitely that is not equal to 1. If I am going to take it as A cross B is equal to 1, so I am getting B equal to 1. So, which is a contradiction. That means A cross B will never become 1. Will never become 1. Of course, G comma cross and A cross B belongs to G, and we have to verify whether A cross B is equal to 1 or not. If it is equal to 1, if I am taking, then I am going to get B is equal to 1. B is equal to 1, which is a contradiction. So, for that reason, if we are assuming whatever A cross B is equal to 1, which is absolutely wrong. Which is absolutely wrong. Hence, we can say that the closure satisfied. That means A cross B belongs to G, and of course, the value will not become 1. So, it is closed under into. Then the another one is associative property. So, for that, the three values we are going to consider A, B, C, and we are going to verify this. And we are going to verify A cross and B cross C is equals to A cross B cross C. We are going to verify this. So for that first one, A cross B cross C, we are going to take it as B cross C, we are going to write it as B plus C minus BC. Then after that, we are going to apply A plus B and next minus AB. A plus B minus AB. What is A cross B is given as A plus B minus AB. Minus AB. So in that way, I am just taking A cross B is A plus B minus A and B. So I am going to simplify this. I am going to get the corresponding values like this. Similarly, we are going to calculate what is A cross B cross C value we are going to calculate. So now A cross B is this one and cross C will be there. Then once again, which is of the form A cross C. So once again, A plus B minus AB. So if you are going to simplify, this is equal to the same whatever we are going to get in equation 1. So from equation 1 and from equation 2, we can say that both are equal, then associativeness is satisfied. Now we are going to verify the commutative property. So commutative property is nothing but A cross B is equals to B cross A. So what is A cross B? A plus B minus AB, and next B cross A is also we are going to take it as B plus A minus AB. So both are same, or else we can write it as A cross B is A plus B minus AB. So this I am going to write B plus A, AB or BA, both are same. So this I am going to get B cross A. So it is into is satisfying a commutative property. Then once again we are going to verify whether it is having a identity element or not. Let us consider E be the identity element. Then A cross E is equals to E cross A is equal to A. Then we can say that E is the identity element. So taking anything, so A cross E is equal to A. Then A cross E is nothing but A plus E minus AE is equal to A. So these two get cancelled. Now E, I am just taking E is equal to AE. Then these two get cancelled. Now A is equals to, see what I am going to take it as? This I am going to take it as E is equals to E into 1 minus A equals to 0. So now the thing is whether 1 minus A is equal to 0 or E equal to 0. So here 1 minus A is not equal to 0 because we are going to consider the element which are not equal to 1. So A and B are not equal to 1. See, if I am taking A minus B is equal 1 minus A is equal to 0, then I am going to get it is A equal to 1. So A is not equal to N means definitely 1 minus A is not equal to 0. So hence I am going to get the only possibility is E equal to 0. E equals to 0. So then E equal to 0 definitely belongs to G. So it is having the identity element and the identity element is 0. So now we are going to verify the inverse. when we are going to say that A is the inverse of A, or A inverse is the inverse of A, so A inverse or A inverse into A is equals to identity element. What is the identity element? Is 0 here. If this is satisfying, then we can say that A inverse is the inverse of A. A inverse is the inverse of A. So for that, we are going to take it as first A cross A inverse. A cross A inverse. So that is nothing but A plus A inverse minus A inverse. Just we are going to write. So this is nothing but, what is A plus B is nothing but A into B. A into B. A plus B minus AB. So that is nothing but A plus B minus AB. Just multiplication. So A inverse we are going to get. Now if I am taking A inverse as common, then I am going to get, so A inverse is equals to A by A minus 1. See here A is not equal to 1. So subsequently it is not an undefined value because A is not equal to 1. So definitely denominator will not become a 0. So some value I am going to get. Subsequently A inverse is equals to A by A minus 1. Definitely it belongs to G. Definitely it belongs to G. So thus we can say that the G is satisfying the closure and associativeness and existence of identity, and the next inverse, and it also satisfies the commutative law. So we are going to say that G and the binary operation is nothing but a abelian group. Is nothing but a abelian group. So what is G here? Q minus 1. Q minus 1. And the binary operation multiplication defined as like this is a abelian group, is an abelian group. So like this we have to do. And the next another one is prove that a group G is an abelian if and only if AB whole inverse is equals to A inverse B inverse. We have to prove that the group is G is a group, G is an abelian group if and only if we are going to prove that AB whole inverse is equals to A inverse B inverse. So for that, see here two cases, if and only if will be there. So first we are going to take it as a G is abelian. G is abelian, and we are going to prove that AB whole inverse is equals to A inverse B inverse. This we have to prove. Then the conversely we are going to take AB whole inverse is equals to A inverse B inverse we are taking, and we have to prove that G is abelian. Because it is a if and only if condition is there. If and only if a condition is there. So first of all, we are going to concentrate this. So first we are going to take given G is abelian. Then we are going to prove that AB whole inverse is equal to A inverse B inverse. So now I am going to take A inverse B inverse is equal to, see here it is G is an abelian. So whatever the values that we are going to consider, A, B belongs to G, and G is abelian means G is a group. So definitely every element will have inverse. So A inverse and B inverse is also exist in G. A inverse, B inverse is also exist in A, and it is closed, under. So for that we are going to take it as A, B inverse, B inverse is also belongs to G. So we are going to take that A inverse, B inverse, A inverse, B inverse, and once it is an abelian, so I am going to write this as B inverse, A inverse. It satisfies abelian property. So we are going to write the commutative law. So I am going to write A B inverse A inverse. So any group B inverse A inverse is nothing but AB whole inverse. AB whole inverse. So we can say that AB whole inverse is equals to A inverse B inverse. A inverse B inverse. So because any group, if I am going to consider AB whole inverse is equals to B inverse A inverse. Okay, this is a if condition. Next, else condition, or if and only if. So conversely, we are going to take this, we have to consider AB whole inverse is equals to A inverse B inverse we are going to consider. Now let us consider, we are going to prove that G is an abelian. G is an abelian. So for that it is given. This property we have to use. This property we have to use. Let us go, and I'm going to take x comma y. Let us any two elements. X comma y belongs to G, and then I'm going to take xy, and y is equal to yx is also belongs to G. Obviously, x comma y belongs to G. G is nothing but a group, and so xy is also belongs to Z because it is closed. Now, I'm going to write x as x inverse whole inverse and y as y inverse whole inverse, because I'm going to write x as x inverse whole inverse, y as y inverse whole inverse. Then I have to use, this is nothing but A inverse B inverse. A, this whole thing is A. This whole thing is A, and this is nothing but a B. This is nothing but B. So I'm going to write A inverse and B inverse. So which is a AB? A is this and B is this whole inverse. But because I'm going to use this. I'm going to use this. So AB whole inverse. AB whole inverse in any group, B inverse, AB whole inverse is equals to B inverse A inverse. So AB whole inverse is equals to B inverse. And next, A inverse. Y inverse, whole inverse, X inverse, whole inverse. So it is nothing but Y, and this is nothing but X. So XY is equal to YX. So it is an abelian group. It is an abelian group. Now, let us go for the other one. Find the number of permutations. Permutations of the letters, word, this word will be there. How many number of permutations of the letters, the word MASSA, SAUGA. In how many of these all four A's are together, and how many of them begin with S? How many of them begin with S? So find the number of permutations. So here there are 10 letters are there. There are 10 letters are there, in which A is 4 times, S is 3 times, and MUG are 1 time. Now the required number of permutations are nothing but, so this is nothing but a total number factorial by the repetition number. So repetition letters, let us say you are going to take it as A is repeated 4 times, then I am N1 time, and I am going to write N1 factorial. And another character is repeated N2 times, then I am going to write N2 factorial. Then another character is repeated 3 times, N3 factorial, and so on. And so on. Okay, how many times it is repeated, the character, those many times you have to write the factorial, So that means in that way we are going to find the number of permutations. So for that, the given word which is having 10 letters, so I am going to take 10 factorial, out of which A is repeated 4 times, so 4 factorial. Now another one is S is 3 times, so 3 factorial, and the remaining are only 1 time, so 1 factorial. Subsequently, we are going to get 25,200. 25,200. How many? Next, another one is, in how many of these? All A's are together. All 4 A's are together. So we are going to take all 4 A's are together as 1 letter, and the remaining are, this is 1 I am taking, 2, 3, 4, 5, 6, 7. So I am going to rearrange. The permutations in such a way that all A's should come only once. So all A's we are going to consider, I am going to group all A's into 1. So then if I am taking like that, there are 7. So 7 factorial by A's are only, I am going to take it as grouped and it is taking as 1. So 1 factorial, and next S is repeated 3 times, then M, and next U and G all are repeated only 1 time. So finally we are going to get the 840. And next, similarly, for how many permutations begin with S? And there occurs A begin with S. So S, how many are there? 3 S's will be there. All 3 we are going to consider S's are only 1. So let us say there are 3 S's will be there. This is 1, and the remaining letters will be there. Remaining 7 letters will be there, I have to consider those 7 letters, 7, 8, 9, 10, and see here there are the remaining 7 letters we are going to consider. And what is the next one is yes, sir. How many of them are begin with yes? How many of them are begin with yes? So here there are 2 yes and 4 yes, and each one of M, U, G. So beginning yes, there occur 9 open positions to fill, where 2 yeses will be there, 4 yes will be there, and 1 M, U, G's are 1. So we are going to take it as 9 factorial, and next the remaining. So if I am taking 1 only, then the remaining 4 factorial will be there, and next because yes are 4 times is repeated, and next yes is 1 we are going to consider, remaining is always it is going to be beginning with yes. Yes, I am going to take it outside, and the remaining only 2 yeses will be there. So 2 yes will be there, the remaining is a 1 factorial. Simultaneously we are going to get 7560. Next, another one is, let us go for the other one. Find how many integers between 1, 10 to the power of 4. 10 to the power of 4 means 4 zeros. 1 and 10 to the power of 4. 10 to the power of 4. Okay. So here, between 1 and 10 to the power of 4, exactly contain 1 8 and 1 9. So here, from these, how many digits will be there? 1, 2, 3, 4, 5. 5 digits will be there. So lesser than this, it occupies only 4 digits, or 4 positions will be there. 1, 2, 3, 4 positions. This is 5 positions, and between 1 to 5 positions, we are having only 4 positions. So now, to place 8, let us say, to place 8 in these 4 positions, any one positions you can say, you can select in how many ways that we can arrange. This is nothing but 4C1 ways. So it is to place 8 in above 4 places in 4C1 ways. 4C1 ways. And similarly 9. See, one place is occupied by 8, and the remaining place, there are 3 places will be there. 9 is going to be placed in those 3 places in 3C1 ways. In 3C1 ways. And the remaining numbers are 8, and in those 2 positions. So to place the remaining 2 places with remaining digits is 8 into 8. First one is 8 possible ways, and the second one is also 8 possible ways. So 8 into 8. So what is the total number of ways are? Total number of ways. So it is nothing but 4C1 into 3C1 into 8 into 8. Subsequently, we are going to get 868 ways. So in these ways, we are going to how many 768 integers between 1 to 10 power 4 contains exactly 1 8 and 1 9 only. 1 9 only. So these are the few question bank problems in this third module, or algebraic structures and combinatorics, and short answers we are going to discuss in the next class. With this, I conclude this. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.